Okay, so hello and welcome back. So in this video we want to talk about the phase shift in basically RL circuits, and basically how that works in an RL circuit. How the phase shift works in an RL circuit is basically something like this. Of course, we are going to do a couple of experiments as well to see how the whole thing works out. But basically we had basically we had two types of RL circuits. So we had basically the type of the RL circuit where you had basically an inductor over here, and then the inductor was was basically connected to a resistor, and then the resistor goes to ground, and this is your basically V of out over here, and this over here is your V of in. And so basically this is a resistor, this is an inductor, and the voltage, the output voltage, is actually the voltage across this resistor. And so the way that your voltage changes with frequency in this circuit is that the more that you increase your frequency, you know that basically in these, basically in the case of an inductor, X of L is equal to 2 pi FL, and basically your Z is equal to the square root of X of L squared plus R squared, and your V of out is basically depends on basically what sort of output. So once you have the output across the capacitor, the resistor, so it's going to be the resistance of that resistor over the whole impedance in that circuit times V of in. So basically this, with frequency, the value of this resistance is not going to change. The only thing that changes is your Z, and your Z is going to increase as you increase your frequency, because your X of L is going to increase as you increase your frequency. So as you increase your frequency, X of L increases, and with that increases your impedance, and once your impedance increases, then the value of this fraction gets smaller and smaller, and you are actually having smaller and smaller fractions of your input voltage at your output. So that means that as you increase your frequency, your output is going to get smaller and smaller, and that's basically what happens. And that's basically what happens in the case of this circuit. If that is F of in, if this is V of out, then that's basically what happens in this circuit. And then that's basically why this sort of circuit is called a low pass filter. A low pass filter. Okay. Now this is basically related to the magnitude of the output voltage for this circuit. But there is also, as you know, there is also the phase shift in such circuits. And the way that the phase shift works in these circuits is that you have if you have basically your input, if you have your input like this, meaning that if your input, let's say that this is let's say that this is pi by 2, this is pi, this is 3 pi by 2, and this is 2 pi, and this is, for example, the upper peak and the lower peak of your signal. Then at pi by 2 you're at 1, and then over here you go to 0, over at 3 pi by 2 you're at -1, and then over here you're at 0. So that means that this is the upper peak and the lower peak of your signal, and your signal is going to be something like this. Of course it's supposed to be symmetric, but the graph is not of course perfect. So this is your input. This is V of in. Okay, so and at basically at theta is equal to 0, your input is actually 0. That's how a sine wave actually functions. But then your output relative to this signal is going to have is going to actually lag, meaning that if this is your, let's say that this is your output, V of out, and let's say that these are the values of pi by 2, pi, 3 pi by 2, and 2 pi. If there was no phase shift, then of course you would have the same waveform over here. But there is always going to be some there is always going to be some phase shift in your output signal. And in a low pass filter where you have an inductor, you're always the output is always going to lag, or the input is always going to lead. And so, for example, you would have some situation like this. So everything is going to be shifted to the right, meaning that this signal is going to lag by, I don't know, 10, 20, 30, 40 degrees or so. So then you would have this kind of situation going on. So then this would be your 0 point, this would be 1, this would be 0, this would be -1, and this would be 0, and then this would be your waveform relative to the input. Okay, so you see that your output is actually in this circuit, your output is lagging, and your input leads your input leads the output. Okay, so that is basically what happens in a low pass filter where you have an inductor. Okay, so that's basically one thing, and I don't really know what these things are. I think we can get rid of that. I can get rid of these as well. And okay, put them over here. So this is a low pass filter. Now you can have another situation like this, where meaning that you can actually build a high pass filter using an inductor. You can build a high pass filter using an inductor, and the way that you do that, so let's say that you have your circuit is this time, instead of having the inductor here, you have the resistor over here. So you have a resistor over here, goes to an inductor, and then the inductor is grounded over here, and this is basically your V of in, this is your V of out, this is your R, this is your L. Okay, so now what happens here, you are actually monitoring the voltage across the inductor, and as we said before, what happens is that the voltage across this inductor V of out, which is equal to V of L, is equal to the reactance of this inductor, which is X of L, by the total resistance on this in this circuit, which is your impedance, times V of in, right? And basically your X of L is equal to 2 pi FL, 2 pi FL, and your Z over here is equal to the square root of X of L squared plus R squared. So now as you increase your frequency, your X of L is going to increase and increase with the increases in frequency. That means that as you increase, and so then the value of this fraction is going to get bigger and bigger, greater than 1. I mean closer and closer and closer to 1. And so because if you have, for example, if you have 1, then I mean if the value of this fraction is 1, then you have 1 times V of in, which is equal to the whole input voltage is going to be output. But then if this is a fraction, I mean the value of the fraction is less than 1 but getting closer and closer to 1, you're having more and more a higher percentage of your input as your output, or across this inductor over here. So what that means is that in this circuit, as you increase your frequency, your voltage is going to shoot up, and that's basically what happens here. Your voltage is going to shoot up. So if this is V of out and if this is F of in, you're going to have some graph like this, and that's basically why it's called a high pass filter, meaning at high frequencies much of your signal is passing through, at lower frequencies much of your signal is being suppressed. So that's basically called a high pass filter. Okay, so now that we know basically what sort of filter we have, and we know that enough information about our output, we also need some information about our phase shift in this circuit. So in this circuit, what happens is that if this is V of in, and let's say that these are the peaks on my signal over here, let's say this is pi by 2, pi, 3 pi by 2, and 2 pi, you're going to have this signal over here. So your signal actually looks like this. So, and then your output relative to your input is going to be something like this. Actually, you can use a ruler or something, or square paper. Okay, so your output is going to be something like this, meaning that if this is your V of out, then basically your output is going to lead, meaning that, for example, this point is going to be somewhere over here, this point is going to be somewhere over here, somewhere over here, somewhere over here, and somewhere over here, and this is going to be 0, and my outputs are at the peaks are going to be here, and this is going to be the new, this is going to be the Actually this is supposed to be here. So you see that your output is leading. So the output leads the input. The output leads the input. That's basically what happens in this circuit. Of course, we are going to do a couple of experiments here to see what happens here exactly with these circuits, using a couple of a simple resistor and a simple inductor. But that's basically what happens here. Now, one important thing that we have that there is also important in this circuit is the vector diagram or the phasor diagram for these circuits, and that's the kind of thing that you need to know as a part of your theory about these circuits. So the phasor diagram or the vector diagram related to these circuits is basically something like this, meaning that you have this becomes your V of L, and this becomes your V of R, and this becomes your V of in. Okay, and this angle over here becomes your theta, and this is the current going through the circuit. So this is your V of in, this is your V of R, V of L, and theta and I. So that's all that we have here. And that's basically in the case where your output is basically on the inductor, which is basically this case over here. And you see that in this case the V of L is actually the V of L, or the V of output, is actually leading the input voltage, which is basically, as you can see over here, V of L or V of out is leading the input voltage, which is basically, as you can see, the same thing you can see over here. V of L is leading the input voltage, and this part is actually the case where the output voltage is on your resistor, which is actually this case over here. And in this case, you see that V of in leads the output voltage, and as you can see over here, your input voltage is leading the output voltage, and this is the voltage across the resistor here. So that's basically, very simply, your phasor diagram. And in this phasor diagram, of course, you know that if you want to calculate this thing over here, tan of theta is opposite to adjacent. So opposite is this side, which is V of L over adjacent, which is V of R. So that way you can calculate it. Also, you can calculate it by x of L to R, and also you can calculate it, your x of L, you know that it's 2 pi FL to R. Basically, these are some ways to calculate your theta, tan of theta, and then theta would be the tan inverse of these ratios. So that you already know as well. And now that we know all of this, we can actually calculate a couple of phase angles over here, and then we are done with the theory part of this theory part here. So I take a few minutes rest, and I'll see you in just a few more. Okay, so now let's try to calculate some phase angles here. So for example, if you have a circuit something like this, so for example, if you have a we have had this circuit before, but when we worked on it, we were working on basically we wanted to calculate the output, I suppose. So this is an inductor, this is a resistor, and this goes to ground. This is your V of out, this is your V of in, and this is 160 millihenry, and this is 1 kilo ohm. This is 1 kilo ohm, and your input is basically at you have a sinusoidal signal, a sine wave, and you're at 10 volts over here. That's 11 volts, and that's 9 volts. So that means that basically you have a 10 volt DC offset over here, and that the signal itself is basically 2 volts peak to peak. Okay, so now you want to calculate the phase angle for this circuit. So the phase angle for this circuit, so of course, and before you do that, you need to know basically what sort of circuit this is. So since you are you're actually calculating the output across the resistor, it's going to be, I think, a low pass filter, because as you increase the frequency, the voltage drop across this inductor is going to increase. The voltage drop across here is going to decrease, and so you will have some, if this is V of out and this is F of in, so as you increase the frequency, the voltage over here is going to decrease, so you will have something like this. So it's a low pass filter. Low pass filter. So now what happens here is that basically you know that the tan of theta here is equal to V of L, and the reason for that again is that basically your let's say that this over here is V of L, and this is V of R, and let's say that this is V of in over here, and this is the current that is going through the circuit, and this is your theta, right? So tan of theta is equal to V of L to V of R, basically V of L to V of R. So if you calculate the voltage drop across this inductor, and the voltage drop across this resistor, then you'll be able to use this relationship. But I think that we will have to do some experiments here to see how this actually works if you had for example, a circuit like this. If you had a circuit like this, for example, a capacitor and a resistor over here going to ground, and if this was V of out, and if this was V of in, the relationship between these voltage drops in this circuit, if AC was coming in, would be V of in squared would be equal to V of C squared plus V of R squared. Okay, so that would be the relationship, but I don't really know what the relationship here is, and so I would have no way to calculate I can calculate the V of R here, but then I could not calculate the V of L here, so that would be, so I'm not going to use this relationship. I'm going to use the other relationship, meaning tan of theta is equal to X of L to R. Because I already know what R here is, I can calculate my X of L here, which is equal to 2 pi FL. I know the frequency, and hopefully the frequency is 1 kilohertz. 1 kilohertz is the frequency, and I know the inductance here, so I can use this. I can use this one over here. Okay. So what happens is that so you know that tan of theta is equal to X of L to R. So your X of L is equal to 2 pi FL, which is equal to 2 pi times F. The frequency is 1 kilohertz, so 1000 hertz times L, which is 160 millihenry. So 160 into 10 raised to the power negative 3 Henry. These two will cancel out, and so you have 2 pi times 160 is equal to 1005.3. 1005.3 ohm here. So that's your X of L. So then your tan of theta is equal to X of L, which is equal to 1005.3 over R, which is basically in this case 1000 ohm. 1000 ohm. So this divided by 1000 is equal to 1.005. 1.005. That's a ratio actually. Okay. So now theta is equal to tan inverse of this ratio, which is basically 1005.3. 1000 actually it's equal to use the whole, if I were to use the whole ratio, it would be tan inverse of 160 times is equal to 320 pi over 1000. Okay, that would be tan inverse of this. So now if I think that was 1.005. So let me see, if I have 320 pi over 1000, it should be equal to somewhere around 1.005. Okay, so now if I calculate the tan inverse of 320 pi over 1000, that should give me the value of theta. So is equal to 45.15 degrees. That's the value of theta. Okay, and what that means is that the value of theta over here is 45.15 degrees, and that's the angle between V of R and V of in. So my circuit was basically over here, so that's the angle of the voltage between V of R, basically this resistor over here, and this input voltage over here. That's 45 degrees. And then we can also do another we can also do another circuit over here. You have another circuit. So let's say that you have another circuit, you have a circuit, basically something like this. So this is an inductor going to a resistor, and that's connected to the ground, and this is your V of in, and this is 320 millihenry, and the resistance is 500 ohm. This is 1 kilo ohm. This is your V of out. Okay, and this is again the same story. This is a low pass filter, right? So again, your tan of theta is equal to x of L to R. I can calculate tan of theta is equal to x of L to R, for example, and that's equal to now x of L here is equal to 2 pi FL, which is equal to 2 pi times F. The frequency is here 1 kilohertz, 10 raised to the power 3 hertz, and L here is 320 millihenry. So 320 into 10 raised to the power negative 3, and these two will cancel out. So 640 pi is your x of 640 pi ohms. So now, and your R is equal to 1000, so this is 640 pi ohm divided by 1000. So that is tan of theta. So then that means that theta is equal to tan inverse of 640 pi over 1000, and that's equal to tan inverse of 640 pi over 1000. That's like this one. That's equal to 63.56 degrees. I think there's something wrong in here. X of L to R, and the circuit is 2 pi FL, so F is, the frequency is 1 kilohertz. That is 320 millihenry. So that's 2 times 320, 640 pi divided by 1000. Oh, sorry, and then you're not supposed to ignore the resistance of this thing over here. So you have actually a 500 ohm resistance over here as well. So that's actually going to be the total resistance in this circuit. So that's going to be 1000 plus 500. So that's 1500. So then the tan inverse of 640 pi divided by 1500, and that's equal to 53.28 53.28 degrees. Okay, so So I need to be careful about this thing over here. I just didn't notice it. So that's basically all there is over here, and then in the next video we will go over we will build a couple of probably a couple of high pass low pass filters using these using some inductors, and then on top of that we will also build a circuit in order to find out what the inductance of some inductors are. For example, you see over here I have all of these inductors. For example, on this it says 100 microhenry. Over here I've pulled this out of a power supply. This is 100 microhenry. That was in some input part of some power supply. And then this, for example, you could find in an ATX power supply. All of these you could find in ATX power supplies. So these are all inductors, and this is also some inductor, but then you see the thickness of the wire over here. This thickness corresponds to the current going through this wire. And there is also these inductors over here, and you need to be able to actually measure these things. And there is something called an RC meter. LC meter. There is something called an LC meter, and an LC meter is basically something like a normal handheld multimeter, but with that you can specifically measure inductance and capacitance and resistance as well. Usually these three are in an LC meter. But of course there is all of these benchtop, for example, inductance meters and so on and so forth. There is all kinds of them, of course. Now I don't actually have an LC meter, and I think I'm going to need one, but before I'll have to actually order one to get one. So I'm going to actually we are going to create one of them together, and then we will do some experiment with that and so on and so forth. And that's going to be probably the next 2 videos. So let's see how that goes. So I'll see you in the next videos. Thank you.